So the standard model of cosmology is based on two fundamental assumptions and axioms. The one is that the Einsteinian-Newtonian formulation of gravitation is valid everywhere. The Newtonian formulation is, of course, only valid in the classical regime. And the second assumption, which is very fundamental, is that all matter is created at the Big Bang. We then add observational data, for example, from the cosmic microwave background, rotation curves, to find that we need to add three auxiliary assumptions, which are inflation, dark matter, and dark energy. And I should note here that the dark matter here can be called warm, fuzzy, or axion. It doesn't matter because ultimately it has to behave in the same way. For example, in this theory, one has to account for little galaxies which have a size of only about 50 parsecs to be dominated by dark matter, which means that fuzzy dark matter must have a wavelength so small that it actually manages to fit into these small galaxies. Therefore, it then becomes very similar to cold dark matter on the scales of a kiloparsec. So we have this model where we have the Big Bang, then inflationary periods, and then the universe expands. And today we are experiencing yet again a new inflationary period through the action of dark energy. As the universe expands, the gas cools. We then see the cosmic microwave backgrounds when the photons decouple from the matter, and during this time, the dark matter is already forming the first gravitational-bound structures into which the cooling gas falls, forms the first stars. The dark matter halos coalesce, forming larger dark matter halos into which more gas falls. Galaxies form, merge, form larger galaxies, and today we would be observing this universe, if this were the correct universe. So there are some uncomfortable properties. The dark matter particles needed in this theory are not part of the standard model of particle physics, and no experimentally verified extension of the standard model of particle physics exists. The dark matter particles have not been found despite an incredibly huge effort by many research teams. Dark energy is totally not understood. Does it constitute infinite energy creation? It is a total misfit to the vacuum energy density. Inflation has many issues, and this was a very interesting inflation debate by these authors published in 2017 in the Scientific American, which you might like to read up on. So according to the standard model of cosmology, galaxies look as follows. This is the observable part of the galaxy, stars and gas, and the galaxy sits in a dark matter halo, which has this type of scale for a Milky Way type galaxy, and the dark matter halo is composed of dark matter particles, but also many subhalos, dark matter subhalos. Again, these are actually black, but here, in order so we can see them, they are shown in a negative image. And these dark matter subhalos are orbiting around here and slowly shrinking downwards to merge with the central galaxy. It's a very dynamic life structure. New dark matter halos fall in as the structure grows. And this leads to us to an immediate fundamental dysfunctionality. 90% of all real galaxies are thin disk galaxies, but we cannot predict their rotation curves. So given an observed mass distribution, it is impossible to calculate the circular velocity of stars within it in the sense of a prediction. Why not? Well, this is here the answer. So here we are plotting on the y-axis the stellar mass of the galaxy, while this here is the dark matter halo mass of the galaxy, and each point here is one galaxy obtained from cosmological supercomputer simulations in this framework. And so, for example, our Milky Way has a stellar mass of about 10 to the 11 solar masses, and so it can have a dark matter halo mass of about 10 to the 12 solar masses, or it can also have a dark matter halo mass which is more than 10 times larger, but we don't know which it is because we can't observe the dark matter. Furthermore, the concentration of the dark matter halo is unknown. So this plot shows the log of the concentration versus log of the visual mass of the dark matter halo. So our Milky Way would have a dark matter halo mass of, say, 10 to the 12 solar masses, and it would have a concentration which is this small, or equally, it could have a concentration which is more than 10 times larger, but we don't know since we can't observe the dark matter. And so this essentially means as follows. We have the observed galaxy, and this galaxy can have some dark matter halo around it within a range of possibilities. It has a concentration, it has dark matter subhalos, and the radius and mass of this dark matter halo, which can be rotating this way or that way, and we don't know. And for this particular case, one might predict this rotation curve or calculate this rotation curve if we know this exact dark matter halo. But then the same galaxy might also have a dark matter halo which has this shape. And then it would have this rotation curve. And it might also have a dark matter halo of this shape, and then it would have this rotation curve. And so we cannot predict the rotation curves from the observed matter. That's the point, in this theory. Now, there is a prediction of a new phenomenon in this theory. If there is dark matter, then there must be Chandrasekhar dynamical friction. What this means is as follows. So we have here a Milky Way type galaxy in its dark matter halo with its concentration, and then another galaxy falls into it. And it also has its own dark matter halo. And as the galaxy falls through the dark matter halo of the host galaxy, this dark matter halo and galaxy interact with the dark matter particles in this galaxy. The interaction is purely gravitational, of course. So each dark matter particle here is deflected by the motion of this galaxy, which is entering the host, and is deflected. And the many, many deflections cause this galaxy to get slower, to slow down. We can visualize this by considering that these deflections cause a dark matter wake behind the galaxy, which pulls back at the galaxy, and so it decelerates. Now, after integrating all these encounters, gravitational encounters with all the dark matter particles, one finds this equation. It's a well-known equation in dynamical friction. And this tells us how the velocity of the galaxy is reduced per unit time. It depends on the mass of this galaxy and its dark matter halo. It depends on the velocity of this galaxy, and it depends on the mass density of the dark matter halo. Now note that the mass of the dark matter particle doesn't matter because it's the mass density which matters. So you can have massive particles or very, very low mass particles, but then you'd have many, many more very low mass particles. This quantity, the mass density of dark matter, is fixed by the cosmological model and the cosmic microwave background. This means that the dynamical friction has no parameter in it which we can tune. So we cannot, in this theory, increase or decrease the dynamical friction process. Once the theory is formulated, as it is now, given the data boundary conditions, this process is fixed. And so what happens is the galaxy falls in, forms a dark matter wake behind it, and falls further in as it loses kinetic energy and falls in and merges. And this is the reason why galaxies merge. But they only merge if there is dark matter. Because without dark matter, we don't have the dynamical friction, and then galaxies just pass each other. Now, this leads to an actual dysfunctional property, and that is that bars slow down due to dynamical friction on the dark matter halo. So we have here this galaxy with a very major bar in it, and this bar rotates like a solid body. And so it forms a wake behind itself as it's rotating in the dark matter halo of this galaxy. This wake pulls back on the bar and slows it down. And this has been studied by the research group of Mahmoud Roshan and Neda Ghafourian and others. And they find that the observed bar rotation to be in 8 sigma tension to the latest high resolution Illustris and Eagle models. So one quantifies this parameter R, which is the length of the co-rotation. So you have a galaxy, and in it is a bar. The bar is rotating like a solid body, and at that radius in the galaxy at which the stars rotate with the same angular speed as the bar, that is the co-rotation radius. And that distance from the center, one divides by the actual bar length. And if this quantity R is larger than 1.4, we have a slow bar. And if it's smaller than 1.4, we have a fast bar. The data are plotted here. So we have here the R parameter, this one here, and this is the dispersion of the R parameter. The observational data are here. So it shows, with this confidence contours here, it shows that real galaxies have fast bars. 1.4 is just over here. But of the theoretical galaxies with dark matter in the standard model, cosmological model, have slow bars, and the difference between the theoretical and the observed bars is an 8 sigma tension, and this disproves dark matter at very high confidence. Now, given that this is a serious conclusion with major implications for all of astrophysics, one wants to confirm this conclusion with independent tests, of course. One doesn't do one single test, but typically one would try to do additional, completely independent tests to see if the results converge. And so here we can test this concept of dynamical friction by compact groups of galaxies, which should merge within 1 billion years. So you have, for example, here a Milky Way type galaxy, which has these other galaxies around it. The M81 group is very nearby. So we have the local group, and then just next door, a few million parsecs away only, it's basically the nearest galaxy group, is this M81 group. So we have good data for this group. You can see that these galaxies have interacted because the radio telescopes tell us that there's gas all over the place, and there's these gaseous tidal tails, like over here and here. And so this type of data tells us that these galaxies have been interacting at least once to pull out the tidal tails, or they've been interacting multiple times. And so you can already see that this might be a tense friction, because each of these galaxies is, in the theory, surrounded by a dark matter halo, which is bigger than this slide, each of these galaxies. And so these dark matter halos are sitting on top of each other and interacting with the galaxies moving around in there. There's massive dynamical friction in here. And so this has been looked at by Yoon in 1999 and independently by Thomson, Lane, and Turnbull in 1999, and they found no solutions with dark matter because these galaxies merge too quickly and they can't distribute the gas as seen. They get solutions without dark matter. The galaxies just orbit about each other, pull out tidal arms and tails, and the gas gets distributed. And we confirmed this in our own work. And basically what one finds is that in order to reproduce the current situation of this M81 group, all the galaxies in the group must have come from a large distance to magically meet at instantaneously, basically at the same time, have one encounter before they merge, when we wouldn't see this group anymore. And so this basically means that this is arbitrarily unlikely. Furthermore, we have many such compact groups of galaxies. And so this supports the previous conclusion. There's no significant dark matter halo in the nature. And so this is important because the conclusions are converging. If they were diverging, if one test would tell us there is dark matter, it's consistent with the standard model of cosmology, while another test would tell us it's not, then we would have a problem. But convergent conclusions are essential in this game to reach the strong conclusions which I reach. So we can continue with the testing by looking at the motion of the large and small imaginary clouds. We have here the galaxy, our Milky Way, with the center of it, Sagittarius, and this is the large and small imaginary clouds. The large and small imaginary clouds are moving past the galaxy with a large velocity, with something like 250 kilometers per second. The large imaginary cloud is at 50 kiloparsecs from the center of the galaxy, and the small imaginary cloud is at a distance of 60 kiloparsecs from the galactic center. They have interacted and also have left a long hydrogen trail, which is called the Magellanic Stream. So these type of data, so this is very similar to what's happened in the M81 group. So this type of data constrain the allowed orbit of these galaxies. So we have the following situation. We have our galaxy here with its dark matter halo. And then we have the large imaginary cloud with its dark matter halo moving past the galaxy, but this dark matter halo is within our large dark matter halo. And then we have the small imaginary cloud with its dark matter halo and within the dark matter halo of the large imaginary cloud and the dark matter halo of our Milky Way. So 3 dark matter halos on top of each other, and you can see that there's a lot of dynamical friction involved. And this is being investigated currently. The work is in preparation, but the results are very clear. There is no solution within the dark matter framework. The current positions and velocity vectors of these galaxies, plus the constraining fact that they need to be close and they must have interacted to give the Magellanic Stream, does not allow solutions with dark matter. Now, this tension is increased even more significantly because the Milky Way has not only these two satellite galaxies, but it has also other satellite galaxies which themselves have their dark matter halos and suffer dynamical friction. And this has been studied in 2011 in this research work here. And again, this conclusion here is that the then known satellite galaxies don't work with dark matter. Linked with this here, it's of course a massive falsification of the dark matter theory. Now we can look at other aspects of how this theory is supposed to arrange matter, because we can calculate it very well in supercomputers. We know how these structures form and the way the subhalos arrange themselves, and so we can observe the distribution, the three-dimensional distribution or the six-dimensional distribution in phase space of satellite galaxies and their equivalent in the dark matter model, and make comparisons. And so this problem was pointed out for the first time in 2005, where it was realized, or actually published, that the satellite galaxies are in a plane much like the planets around the sun. And then after that, Marcel Pawlowski and Oliver Müller significantly increased the research effort on this problem. And here's one figure from Pawlowski et al., which shows now a region of spanning 1 million parsecs times 1 million parsecs. And what we are looking at is, we are looking down from the North Pole downwards onto the Milky Way disk. You can see the Milky Way disk here. And its satellite galaxies are in this plane, forming a thin plane. And we are seeing also Andromeda. Andromeda is this ellipse here, and half its satellite galaxies are in an even thinner plane. And the remarkable feature here is not only that these galaxies have these satellite planes, but furthermore that the satellite plane of Andromeda is pointing at the Milky Way, and in addition to that, both planes of satellites are rotating in the same sense, which means that there's an incredible amount of correlation between these two satellite systems. So how can the Milky Way and Andromeda satellite systems be so correlated if there are subhalos falling in individually? So the idea and the theory is that all of these satellite galaxies have their own dark matter halos, and they fall in and merge with Andromeda, adding to the mass growth of these galaxies. But in that theory, it is absolutely impossible to have such a correlation between these two satellite systems. To make it worse, Müller-Pawlowski et al. Published the paper, A Whirling Plane of Satellite Galaxies Around Centaurus A. Centaurus A is again a very close by group. So we have the local group, then we have the M81 group just a few million parsecs away, and very close again, just a few million parsecs away, is Centaurus A with its associated galaxies. And the Centaurus A galaxy has a large population of satellite galaxies around it, which is in a thin plane, which is rotating. This proves that Milky Way and M31 planes of satellites are not unique, so this is not a looks elsewhere effect. In fact, since all the major galaxies in their very nearby universe where we can get such three-dimensional data seem to be in such planes, it shows that the planes of satellites are the rule, not the exception. And so combining the probabilities, so these are doing tests of these observed structures relative to the standard model of cosmological simulations like Millennium and Illustris, shows that there's a 5 sigma falsification of the dark matter models. And there's no significant dark matter halo around the Milky Way. So the Milky Way could not have formed from many mergers of subhalos because the remnants of this merger process is simply not evident on the sky. Making it worse, we now zoom out and look at the whole local group. So we are seeing here is everything we know about the local group. This is a region of space of 3 million parsecs times 3 million parsecs. This encompasses the whole local group. The whole local group is defined by all those galaxies which are gravitationally bound to each other. If we go beyond the local group, we find the Hubble flow. What we are doing here is we are looking along the line joining Andromeda and Milky Way. Andromeda and Milky Way, that's just here. So this here is Andromeda, and this here is the Milky Way. These are the satellite galaxies of both galaxies. All other galaxies in the local group are arranged in these two planes, which have a thickness of about 50 kiloparsec and are about 2 million parsecs across. The system is very symmetrical because the distance of this plane to the center to this line is equal to the distance of the other plane. So we have the line joining Andromeda Milky Way, and all the other galaxies which are not satellite galaxies in the local group are in two planes which are arranged like this, symmetrical around the line joining Andromeda and Milky Way. And this whole structure is moving like that relative to the CMB, which is this arrow. You see everything else is empty. And I call this a frightening symmetry because to my eyes this is frightening. How can nature produce such a crystal-like structure on a scale of millions of parsecs, which is a Hubble time old? Clearly this is not the smog at infinite sigma confidence. Zooming out even further, now looking at the region around us of 16 times 16 million parsecs, where the local group is just in the center here, and each point is a galaxy, we find that the local void is too empty, and large massive galaxies are too far from the sheet. So we have here the sheet, the void is far too empty, and there are massive galaxies which are far too far away. These are Milky Way mass galaxies, roughly. Now, the problem is that according to the standard model of cosmology, massive galaxies need to be in the sheet because that is where the matter is from which they form via mergers. So there's nothing here for them to form, but they are still star forming, so they're obviously growing right at this moment. And now we come to actual real cosmological scale tests, looking at massive colliding galaxy clusters at a high redshift. So we have here the Bullet cluster and the El Gordo cluster. The Bullet cluster is at a redshift of 0.3 and has a mass of 1.9 times 10 to the 15 solar masses. There are two clusters which have penetrated each other and gone out again and left the gas in between. So we can see this bow shock. This is the X-ray emitting gas here after the collision. The gravitating mass is shown here in blue as obtained from a weak lensing analysis around these clusters. Then we have the El Gordo cluster, which is at a redshift of 0.9 and is 10 times more massive than the Bullet cluster. The El Gordo cluster again has two clusters which have collided and penetrated each other, leaving this double lobe of X-ray emitting hot gas. And the question now is, within the standard model of cosmology, can one produce such clusters at these high redshifts? And this has been studied by Elena Asensio and Indranil Banik to a great extent. So the question or the problem to be answered is, we start at redshift of 1100, where we see the CMB, the cosmic microwave background. This gives the initial conditions for the cosmological model and structure formation. We then evolve the universe, use the big Jubilee supercomputer simulations for this, to see whether along the time as the universe evolves, one can find such massive clusters. And the result is that it doesn't work. In fact, the existence of these two clusters falsifies the standard model of cosmology with more than 6 sigma confidence. The details are in this publication. We can now perform another cosmological scale test. We count now the matter density as we go outwards from the local group. So on this axis, we have the distance from the local group out to 800 million parsecs. And we measure, as we go outwards, the mass density of galaxies. So per unit volume, how much mass is in galaxies. And as we go outwards from the origin here, we see that the matter density increases, reaching at a distance of about 400 million parsecs, the average density which the universe is supposed to have. This gray region indicates the allowed range in the standard model of cosmology, and what we observe is a massive underdensity on a scale of something like 400 million parsecs. This is called the Keenan-Barger-Coe void, And Modest Hasselbauer and Irel Barnick have been studying this to a great extent. And so in this research publication, the question is, we want to test how often does a KBC void occur in the Standard Model of cosmology. For that one, we used the Millennium XXL supercomputer simulation, one of the largest ones ever performed, with a span here of a box of about 4.2 gigaparsecs. And you can see, so this is now the snapshot at redshift 0. So this is the local universe. You can see here there are underdensities which actually do form. And there are overdensities also which form as a consequence of structure formation. And to answer this question, one constructs a volume with a radius of about 400 million parsecs and measures the amount of the mass density within this volume and compares this mass density with the average. And one does this 1 million times or so. And this is the distribution of these density fluctuations. So that's the frequency, and that's the density contrast parameter. You can see 0 means that the volume is at the mean density. If it's at this point, it's an overdensity in the volume. If it's at this point, it's an underdensity in the volume. Okay, so this is the distribution which is allowed by the Standard Model of cosmology. And that's what the real void actually looks like, with a much, much more pronounced underdensity. The difference between the theoretical distribution and the observed void is a difference of more than 6 sigma, which means that the Standard Model of cosmology is falsified with this test at more than 6 sigma confidence. So we have the void, and we are ourselves in the void, not at the center, but somewhere about a third or so, maybe halfway out. Now, from the void, we can see that the galaxies are falling towards the void edges, towards the void walls, because the gravity pulls them there. So from our point of view, the universe appears to be expanding more rapidly, which means that the mere existence of this KBC void automatically solves the Hubble tension. The Hubble tension is not a tension, it's actually a logical consequence of the fact that there is this void. However, this does not help the Standard Model of cosmology because the KBC void is not possible in the Standard Model of cosmology. And this is what we've tested. We've taken the boundary condition, again being the CMB, moved to the present time with the Millennium simulation, as I've just described, and found that such underdensities on that scale, 400 megaparsec radius, are excluded in the model at more than 6 sigma confidence. Note that Kenworthy et al. Argue that the KBC void is not possible because they don't see evidence for this motion, this expansion in the supernova 1A data, but they made an error in the analysis. And that error is discussed and explained at length in Hasselbauer et al. 2020. So this massive underdensity on this large scale is seen in quite a few other surveys. We see it in optical galaxy surveys. We see it in the infrared. Of course, that's where the name comes from. We see it in X-ray cluster surveys, and we see it in evidence from the CMB dipole of large-scale bulk flows expected for such a void, and there are these publications which report that. Furthermore, there's much evidence for highly significant over and underdensities in galaxy cluster data. This is the nice work of Mikas et al. And there's also 4.9 sigma exclusion of the cosmological principle based on the distribution of 1 million quasars by Sekres, Sarkar et al. And so there is no dark matter. This is absolutely clear from the data. Galaxies therefore merge very rarely, if ever. I mean, to merge a galaxy, they'd have to really physically collide in terms of the physical observed matter. And what about dark energy? So the evidence is thus that the real universe is far more structured than allowed in the Standard Model of cosmology. As the universe evolves and these voids build up and also overdensities build up, a larger and larger fraction of the universe is occupied by these voids. The voids expand more rapidly, which means that an observer within the voids will see as the voids reach a critical fraction of the volume that the universe appears to suddenly start to accelerate its expansion. And this has been shown by David Wiltshire. So cosmic acceleration is an apparent effect due to the over and under densities in the universe, which are far greater than allowed by the standard model of cosmology. Now, it's basically the same effect as the Hubble tension, which is an apparent fast expansion, except it is on much larger scales. Observed from a deep void, the universe is older than viewed from a galaxy cluster. And so there doesn't seem to be dark energy. And what now? We have to now turn to non-dark matter theories. The observed lack of dynamical friction, so from the tests I've just mentioned, plus the observed much larger density contrasts on large cosmological scales clearly show that we need an effectively stronger gravitation to describe what's happening out there. But all hybrid and other approaches which mimic the success of the standard model of cosmology on large scales, larger than 50 million parsecs, for example, through dark matter, are immediately ruled out with equal significance and the standard model of cosmology by more than 5 sigma, by the mere fact that we have the void, KBC void, and we have these massive clusters. I'm very sorry for this. This is one is not doing this on purpose to rule out theories, but that's the job of our scientists to learn how the nature works on the basis of the data situation. This leaves only a few possibilities. For example, modified gravity. It's a covariant modification of Einstein gravity. The theory introduces 2 additional scalar fields and 1 vector field. So it's an approach, an attempt to explain what we observe without dark matter. And this has been studied in this research paper by Hossein Haggi and Akram Hassani Zunusi et al., based on dwarf galaxies. Then there's emergent gravity, which essentially means that gravity is a consequence of the information associated with the positions of material bodies. And this has been studied by Lely et al. In this research paper. And then there are the gravitational dipoles idea, which I actually like very much. It's that if antimatter anti-gravitates, matter-antimatter pairs resulting from quantum vacuum fluctuation would be virtual gravitational dipoles. And this, so the dynamic discrepancies in galaxies are an effect of gravitational polarization of the gravitational dipoles. And this has been studied by Barnick and myself using solar system data. And then there's the scale invariant GR, so which is based on Wales integrable geometry endowed with a gauge scalar field. And this has been studied by Indra Barnick, myself, using just the Earth and the Moon system. And so as a summary of these non-dark matter theories, we can say that emergent gravity is significantly challenged by the radial acceleration relation data. Modified gravity is falsified with more than 5 sigma confidence based on the properties of dwarf galaxies. Gravitational dipoles is falsified with much more than 5 sigma confidence based on solar system data. And as the scale invariant GR is falsified with more than 200 sigma confidence based on the Earth-Moon motions and dynamics. And this leaves us now with Mond and Milgromian dynamics, which is a generalization of the solar system dynamics to the scale of galaxies. A formulation in the classical limit is known and is energy and momentum conserving. So in this seminal paper by Bekenstein and Milgrom, they write down the Newtonian Lagrangian of the gravitational field. Generalized, so they write the most general modification of this Newtonian Lagrangian is this form. So you can see that this term has been replaced by this term, where f is now a function of this gradient phi squared. Extremizing the action of this, one can find the generalized Poisson equation. We've seen this before. This is the mass density of the observed matter, and that spawns this field phi. Now, such a generalized, such an equation is known from some classical theories of quark confinement. This function mu, which transits the gravitational law from the Newtonian regime into the extremely weak field regime, can be derived from the quantum vacuum, as shown by Milgrom. Very important is to note that Mond was motivated by the flatness of a few Milky Way type galaxy rotation curves known prior to 1983. This is very analogous to Newton being motivated by falling apple and the moon's motion. The predictions of rotation curves for low surface brightness galaxies were successfully verified much later. At this time, these galaxies were not known to exist, and yet the same theory explains exactly these galaxies. It is wrong to claim that MOND is phenomenological and was designed to only fit rotation curves. This is a wrong statement. It is wrong to make that statement. So what is MOND? Is it a new symmetry? Milgrom discusses the space-time scale invariance properties of it. One can argue that Einstein's GR is completely valid, and only in the extremely weak field limit are the equations of motion changed by process in the quantum vacuum. There's an analogy on this, which goes back to hydrodynamics. Imagine that you've got a trampoline and you put weights on it. So we make this graph, depth versus the weight which we put on the trampoline. And so we have heavy weight, less and even less weight. So the heavy weight creates a large depth here and a lightweight, a smaller depth. We make a model. That's our model of this dynamics here. And then the question is, if we extrapolate this to very low masses, will this work? Of course, it won't work because molecular forces begin to play a role here. And this is reminiscent of what we see in nature. So this plot shows the theoretical acceleration here and the observed acceleration here. For example, we look at Jupiter and we can calculate the acceleration on Jupiter from the sun because we know the mass of the sun, right? So this is this number here. Then we observe the orbit of Jupiter and we can calculate the acceleration needed to keep it on a circular orbit, and that's this number here. The solar system, of course, is exactly on the one-to-one line here because Newton derived the theory based on these data, and Einstein had no other data too. If we now extrapolate the Einsteinian Newtonian gravity law to very, very low accelerations, we see these departures here in the galactic regime. This is the radial acceleration relation. It is completely predictive. There are many publications, so we've seen this before. By solving this equation for the observed matter distribution, one can even derive these wiggles in the rotation curves, which is not possible in the dark matter framework. The planes of satellites are easy as pie. We have interacting galaxies, not merging galaxies, but interacting galaxies that throw out tidal tails from energy and angular momentum conservation. In these tidal tails, new dwarf galaxies form, as seen here. And once they form, what can they do? They have to orbit in a plane, and that's what makes these planes of satellites. The KBC void and Hubble tension is not even an issue. You take the boundary condition of CMB, do a Mond cosmological calculation, and you get such voids for free. Plus the tension, of course, is automatically covered because of the void. L. Gordon bullet cluster, trivial, exactly the same. You just form them in a Mond cosmological model. Because gravity is effectively stronger, so more quickly can one build larger density contrasts. And so the equations of motion in Mond account for observations on scales from 100 parsec to gigaparsec without parameter adjustments. And this is a most remarkable success of modern astrophysics of great historical meaning. There are Mond predictions. So for example, on a scale of less than 100 parsec, one can look at wide binary stars. So Xavier Hernandez has been looking at this with these research papers. The idea is that if you observe very wide binary stars in the galactic field, they should show the effects of Mond by being effectively stronger gravity, so the motion should be faster. And this is being readdressed by Indra Nibanik with these research papers, and I think there will be much to be heard of in this on this topic in the near future, given the Gaia data. There's a prediction of a new phenomenon which is called the external field effect. So we have here a galaxy with stars and gas around it on a scale of 50 kiloparsecs times 50 kiloparsecs. And if we plug this distribution into this equation here, into this row, we can calculate the Milgromian potential, which then tells the gas and stars how to move. We can rearrange this equation into this form, and if we then take the divergence of this potential, subtract the observed stars, stars and gas, the normal matter, we get the phantom dark matter density, which is shown over here. So the galaxy which you see here spawns around it a halo of mathematical halo of particles, which are not real particles, which is spherical, and has it is a logarithmic halo. It also creates some phantom dark matter halo in the disk. So a galaxy spawns around it a phantom dark matter halo, which are not real particles, it's merely the external Roman gravitational potential. And so we can calculate the rotation curve precisely just from the observed matter. If we now put another galaxy next to this galaxy, the dark matter halos shrink, this phantom dark matter halos, and the rotation curve decreases. And so halo shrinks and galaxies become Newtonian. Rotation curves decrease at large R when other galaxies are nearby. So we can formulate an observational test. Is the shape of the rotation curve correlated with the amount of matter around a given galaxy? And this has been looked at by Hossein Hagi and Akram Hassan Zunuzi, finding evidence for this in 2016, but then readdressed by He in this research paper in 2020, where they used very, very fine superior observation data, and they find an 8 sigma detection of this effect. So the inertial mass remains unchanged, but the gravitating mass depends on the surrounding matter distribution. This has the implication that systems which should be round become droplet shape, and this has been studied by these people in 2010-2017 by Xu-Fen Wu and Hongsheng Zhao, and readdressed by Guillaume Thomas in 2018. Effectively, a globular cluster further away from a galaxy or a dwarf elliptical galaxy would not be spherical, but would actually achieve a teardrop shaped, and this can be tested with observations. Simulations are being performed. Graham Candice is leading a cosmology group in Chile to do Mond cosmological simulations, and in Prague, Bonn, Strasbourg now, we're doing galaxy formation simulations. So you take a post-Big Bang gas cloud, allow it to collapse, it has angular momentum, it forms automatically exponential disk galaxies, which are on the radial acceleration relation. And we are now doing cosmological simulation. So you see here 2 boxes. They are initially identical. It's a span of 10 times 10 million parsecs, filled with gas, post-Big Bang gas. And in this case, there's an external field from a larger structure nearby acting on this volume. And you can see the difference. 200 million years after start, the first galaxies begin to form. You can see how galaxies appear in this simulation. In these sheets, voids form. The same on the right. But you can see that on the right, we have fewer galaxies and lower mass galaxies. And so in Mond, structure growth self-regulates through the external field effects. And this is a newly discovered process affecting structure formation, studied by Hasselbauer and Barnick. Very important, the CMB can be modeled in a relativistic Mond theory in which gravitational waves travel at the speed of light. And this is profound mathematical research done by Skordis and Zložník in Prague. And so the conclusions here are that we have many tests, and all of them are a complete and utter and total disaster for the standard model of cosmology. Mond sails through, it seems, perfectly. There are some question marks where research still has to be done. The standard model of cosmology makes a prediction, which is Chandrasekhar dynamical friction. It's a failure. We don't see it in the data. Mond makes a prediction, which is the external field effect, and it's a massive detection and a failure for lambda CDM because the effect cannot exist in this theory, and yet it's observed. And now a naive question. Put on your seatbelts. Is the CMB really the CMB? This is where panic and havoc breaks out in the community. The CMB is sacred. So the first stars formed in dense clusters. We've studied this in this paper here by Yarabkova. And in this paper where we show that quasars and supermassive black holes very, very trivially actually form in the universe. And what happens is the following. So 200 billion years after the Big Bang, the first star clusters are composed of these massive stars, and also low mass stars most likely, but in a very compact configuration, less than 5.5 parsecs, and they are in binaries. Now these will merge. So within much less than a million years, the stars merge and throw out matter. When two stars, massive stars merge, they throw out matter which is nuclearly processed, so already enriched in heavy elements. And then the matter is blown out through the radiation field and winds of these massive stars, and dust forms. So today we have dust between the galaxies, ancient dust, and the dust absorbs starlight from the galaxies and re-radiates it in the infrared. And this has been measured. So we see here the observed extinction magnitude versus redshift, as documented by these people here and in this paper. And you can see that as the redshift, as you go to higher redshift, you see that the universe seems to be getting more and more opaque. Then Wawrzyk took exactly this dust and calculated all the photons which come from this dust, the infrared photons in an expanding universe, and finds in Prague that the sum of the photons across the universe from this dust makes the CMB, including all these fluctuations. Now, and there's a video which explains this research paper by Wawrzyk, which you can look at, by Rachel Parziale. So the cosmological dust origin of the CMB may be supported by CMB anomalies. You can see here in this paper by Schwarz and Starkman et al., they report 3 anomalies. There's a lack of more than 60-degree correlation. So you look at the CMB and the fluctuations are correlated, but once you come to angular separation of more than 60 degrees, there's no correlation anymore. There's a mutual alignment of the lowest multiple moments, which is also seen in supernova 1A data, and there's hemispherical asymmetry, also seen in galaxies. Now, 1 and 3 may be solved by dust because dust forms after the Big Bang, while if the CMB is of inflationary origin, you expect all scales to be correlated because they were causally connected. But if dust forms after the Big Bang, then you get these scales to be non-correlated. And 3, of course, you would expect one side of the universe to be maybe a little bit dustier than the others. And so this has very, very deep and fundamental implications for cosmology, of course. And so that's why this would cause and causes panic. And now I'll come to the epilogue. So we have a problem. The problem is neither the data nor the theories, but it is sociological. The standard dark matter-based cosmological model is the most falsified model which the very vast majority of scientists have ever believed in. Never in the history of humankind have there been so many modern Ivy League educated researchers who have together erred so badly. This is a completely unique scientific crisis in history. The robust falsification of the standard model of cosmology is not new. In 2010, we published this paper, Local Group Test, and in 2012, this paper was published, which is called Falsification of the Current Standard Model of Cosmology. In this paper, I put up this graph. So this is the log of the confidence as a function of time, and this is where the model was created or thought up, formulated mathematically. In 1980, there were the first failures. We had to include dark inflation and dark matter. And then there were 2 real failures, and then we had to include dark energy. So in total, the steps down are 22, but only 19 count as failures because these black ones count as evidence for new physics. Now, if we are very conservative and assume that with every step downwards, we lose 50% confidence in the model, then by 2012, the remaining confidence was 1.9 times 10 to the minus 6. Which means that by 2012, the dark mainstream was well sunk already. And then we have to add the recent falsification based on the KBC void, Hubble tension, El Gordo cluster, bullet cluster, which each individually are more than 6 sigma falsifications. Independently of this, Eleonora Di Valentino has been investigating cosmic discordance and found that taken at face value, the Planck data provide a significant indication against the flat lambda CDM scenario. Not fitting practically half of the current cosmological data is undoubtedly a significant blow to the LCDM model. And for a comprehensive review of the Hubble tension, they wrote this remarkable publication, and they write that there is a strong need for an alternative physical scenario beyond lambda CDM. And so we have the most falsified physical theory ever in human history, which is still believed by the majority of physicists. This may well be the greatest scientific crisis in all of history. Here's an example. In July 2014, this particle physics booklet was published. This is a regular publication which lists all the particles, their excited states and interactions, and there's a long section on dark matter here. It states in the first sentence that the existence of dark matter is by now well established. In 2015, I wrote to the editors and authors and suggested to amend this statement with this statement: the existence of dark matter is a leading hypothesis. This is a true statement. This is not a true statement, but my suggestion was blatantly rejected. It seems that respectable physicists today know dark matter exists. And so the question to ponder is, what is the role in the stagnation of over-invoking authority, Ivy League institutions, hierarchies, prestigious awards and prizes, extreme competition for research money, prestigious journals? One can put up this graph. Here I have discovery of new laws of nature per unit time per active researcher versus time, and today we see that the society is becoming more grant and award oriented, and I think there's an anti-correlation. I think today scientists appear preoccupied with getting awards and grants. And so you can believe in dark matter, but it doesn't matter in the real universe. The first ever detection of doesn't matter. And what does matter is Milgrom's generalized Poisson equation, which underlies the beauty of galaxies and the real richness of the universe. And with that, I want to end by wishing you na zdraví, to the restart. So thank you.